Good evening, ladies and gentlemen. Thank you very much for coming to this public forum on such a hot day. I really appreciate you putting your time into this, even though some of you are here already. So thank you for coming. My name's David Bruce. I'm from the University of South Australia. I'm also an adjunct faculty member for ISU. So I welcome you to both of those institutions here and now for this remote sensing forum on the public benefits, or not, of remote sensing. This evening we have a number of interesting national and international speakers, and I'm going to very briefly introduce them, but they're going to introduce themselves because they're more interesting than I am. So I'm David Bruce, as I've already said, and our panellists, Professor Scott Madry. Scott's going to talk to you a little bit, and Scott is also the director of this summer school for ISU, and he'll tell you a little bit about that.
Welcome. I am Scott Madry. I have the great pleasure of being the program director of the ISU Southern Hemisphere Summer Space Program, which is currently ongoing here in your lovely city. We're having a great time. Our students are back in the back. Give a wave, guys. Everybody knows where they are. That's the team. We have 37 from 11 countries around the world. And we're here for 5 weeks, and we're taking it very easy. We're not working very hard. We're having lots of fun, and it's a great program, and we're having a wonderful time here. I am a remote sensing professional. Do I do my little shtick now? Okay, look out. David asked us to convey what got us into this, what got us started. And strangely enough, I am by profession an archaeologist. I have all of my degrees are in archaeology. I'm a specialist in Old World prehistory. I work primarily in Western Europe and mostly in France. And so for over 30 years, I've been doing archaeological survey in France and doing a lot of aerial survey. And I'm a private pilot, and we fly many hours in the summers with a lot of bumps and bounces, and looking out the window, looking for archaeological sites to then go and try to identify. And I've done this for many, many years, and it's always been very frustrating because it's very difficult and haphazard. And so our access to space has really revolutionized the kind of work that I as an archaeologist can do. And so now I've been involved for many years in the application of space technologies, of GPS, of geographic information systems, primarily though high-resolution satellite imagery, and refining the technique to be able to actually locate archaeological sites using space assets. And I've done much research in this field. Sometimes it's called armchair archaeology, which is hardly true because it's much more work than that. But I want to show you just a couple of examples of what we can do. This is a satellite image of my research area in France. And I don't know if you can actually see it, but here we see a road. This is a 2000-old Iron Age road intersection here. And here you can see some disturbances in the field, and this is an Iron Age habitation, again from about 2,300 years ago. And with a little bit of digital image processing, we can pull out a variety of the various different kinds of features. We map them with GPS, and then we go out in the field. This is a Roman road, originally built by Augustus. You can see the pattern in the soil here. And right here is a round feature, which is a Roman, sort of a watchtower along this Roman road. And one of the things that I can do, I've actually been able to locate over 100 brand new archaeological sites in my office in North Carolina at the University of North Carolina by virtually flying over my research area. I mark the positions with GPS, and then we actually go out in the field and map these sites in the field. Here's another just very quick example of a couple of very large circular features that you can see here. And here's an enlargement of this. This is a medieval 11th century fortified farm. And here we are out in the field. This is all pottery sherds here. This is all 11th and 12th century pottery sherds. And I don't know if you can see it, but there's a ditch and then a slightly raised location here. This is a beautiful site that we located 3 or 4 years ago, and this is a Bronze Age, 2,700 years old burial area, funeral area, and after a little bit of digital image processing, you can see the round features of these tumuli, we call them, these tombs, and there's a series of 11 of these tombs here in this field that were never discovered before, and I found these things in my sitting in my laboratory in the United States. So I have been able to locate over 100 brand new archaeological sites that contribute significantly both to our knowledge of prehistory, but also it allows us to take steps to preserve these important cultural relics that we have. So that's my very brief introduction to one practical and hopefully interesting utilization of remote sensing for you. Thank you.
Thank you, Scott. Kimberly, would you like to step up and introduce yourself? Kimberly Clayfield is in the CSIRO, and she's going to explain what motivated her to get involved in this particular industry.
Hi, everyone. I'm from CSIRO. I'm the Executive Manager of Space Sciences and Technology there, which is in our Astronomy and Space Science Division. I've probably been interested in space ever since I started reading science fiction novels as a kid. And that actually led me into mechanical engineering, which is what I studied originally. I studied here in Adelaide at the University of Adelaide. But I became a lot more interested in the policy side of things in particular in relation to space after I started getting involved with the student branch of the American Institute of Aeronautics and Astronautics, and I attended some conferences like the Space Generation Summit in 2002. So from there I have since acquired additional qualifications in space science and in public policy, and I also have an MBA now. I actually worked in the space policy section of the Department of Industry after I finished my PhD in mechanical engineering. I worked there for several years before I moved to our National Research Agency, CSIRO, and there I primarily provide space policy advice and strategic coordination and development of space science activities across CSIRO.
Thank you, Kimberly. Anthony Wicht is from the Space Policy Office where he's the Assistant Manager from Canberra, and he's going to say a little bit more about his exciting background.
Well, who's heard of the Space Policy Unit? Oh, wow. Who's heard of me? Good. It's always better when more people have heard of the Space Policy Unit. I'm going to tell you a little bit about both because not everybody knows about either. The Space Policy Unit, sadly enough, is probably the closest thing that Australia has to a space agency. It has 8 people. But it performs a really important function, and we'll talk a lot more about this evening. But it serves as the point of contact for our international partners and coordination domestically of Australia's space activities. And remote sensing, which we're going to focus on this evening, is only one aspect. There are a great number of Australian researchers who are involved in all aspects of space activity here in Australia. And part of the job of the Space Policy Unit is to pull those researchers together and really recognise what a nationally valuable capability we have. As the name suggests, the Space Policy Unit is involved in, yes, space policy. We've prepared one document already, glossy copies of which are sitting down here and which I'll proudly tell you about in a little while. But I've also been very busy preparing what will be Australia's first truly national space policy that will articulate what Australia hopes to do in space, and more importantly, why we hope to do it, because we think there are good reasons for Australia being involved in certain aspects of space activity. So how did I end up there? A misspent youth saw me do law for a while, for which I apologise. I did 3 years in a large corporate law firm. I still have some of the pinstripe suits from then. But then I decided that life was too important to be spent working on other people's deals, and that what I really wanted to do was build spaceships. So I went across to the United States and did some work there for a few years until the Boston winters got too much, and I came back here about 1.5 years ago. And this kind of history of going from one thing to another and being flexible and negotiating various bits and pieces was the perfect background to come here and start hammering out Australia's national space policy. So thank you for coming along, and I look forward to talking to you in more detail about the sorts of things we're hoping to do in a little while.
Thank you, Anthony. I'm going to introduce George Dyke, who is an ISU faculty member as well, and a consultant in the space industry with so many connections and so many different things. We don't know how to describe him. So over to you, George.
Undescribable. I'll take that. Hi, my name is George Dyke, and I've met some of you already just chatting beforehand. I'm based in the Blue Mountains in Sydney. I've been living in Australia for 8 years now, but I'm from Canada originally, from Newfoundland. And back in Canada, I studied mathematics and mechanical engineering. That's my education. I started my working career on the space station program, working on the Canadarm2, which is the robotic arm that has built and maintains the ISS. And when I moved out here, I got involved in a small consultancy, and what we work on now is optimizing the utilization of Earth observation satellites around the world, so making sure that user communities are getting served. Our clients are the space agencies. We're working now for NASA, ESA, the Japanese, etc. And so we'll get into a lot of that this evening, I hope, and I'll say a little bit more about the international coordination work that we do, and as well for the students who are going to be at the lecture tomorrow morning, we'll also talk a lot about what we do. But broadly, it's trying to make sure that these satellites are optimally applied to public problems. Professor Bruce asked that we share a little bit about the moment that captured our space imagination. So as I said, I'm from St. John's, Newfoundland, and when I was 9 years old, there was a forum, not unlike this, in Memorial University in St. John's, and we had Mark Garneau and Bob Thirsk come and speak, and my mum took me along to that, and they were talking about this new space program. This was in the 80s, and they were talking about building a space station, which eventually became the ISS that I eventually started to work on. And Mark Garneau was the first Canadian to fly in space. Not long after we saw him talk, he became the first. And Bob Thirsk also flew in space and was the first Canadian to do a long-duration ISS spaceflight, and he's also a very good friend of ISU. He comes very generously. It takes weeks of his time to come and visit. So that was my space moment. There's a small historical footnote, and that is that Newfoundland is halfway around the world, and I don't actually mean that in general. I mean, if you launch in a polar orbit from Woomera over the North Pole, the first place you cross over on the other side is Newfoundland. St. John's is where you fly over. And my grandmother was actually from Adelaide, and she married a Scotsman, got on a boat after the Second World War, sailed to Scotland, sailed to Newfoundland. Some things happened. I was born, and now I'm back. So that's my story.
The format for this evening will be that I'm going to give a very brief introduction as to where space technology is in 2013. We're then going to look at Australian international trends in space remote sensing policy, particularly drawing on Kimberly, Anthony's and George's experience. We want you to interact with that. We're then, time permitting, going to take one example of space remote sensing applications, and we're going to get Scott to lead that discussion and talk about benefits and possibly other things. So very quickly, where are we in space in 2013? What we've seen is a big change in technology, and I've picked 4 sensors to highlight that. In 1972, Landsat 1, which was called ERTS, was launched. It had 60 to 80 metre pixels, 4 broad spectral bands. It had an 18-day repeat coverage, and meaning 18 days to come back to the same spot on Earth, provided the clouds are free to re-image it. It had 6-bit quantization, and it imaged 185 kilometres at a time in a chunk. Move on a few years. In 2000, we saw a significant leap in technology with the introduction of the Hyperion satellite, 30-metre pixels, not massive change in pixel size, but a big change in spectral discrimination with 220 really narrow spectral bands, similar temporal resolution of 16 days to the Landsat. And I put maybe there because it's very difficult to get Hyperion imagery. Certainly you can't get it every 16 days now. It was 12-bit quantization and very narrow swath width. So we see the trade-off between swath width and spectral resolution there. In 2003, an instrument was launched which followed on from the AVHRR series called MODIS. And there were 2 of these, MODIS Aqua, MODIS Terra. And this, I think, is one of the most significant pieces of technology in space because it gives us daily repeat coverage of our whole planet, or most of our planet, with 36 spectral bands between 250 and 1,000 metres spatial resolution and lots of bits to look at the intensity of the imagery. So I think that's pretty remarkable. It's still flying and it's still providing images, and I'll show you one in a little moment. And then we bumped right through to 2011, 2012, 2013. Astrium and DLR, particularly Astrium in this case, have launched Pleiades instrument. It's multispectral and panchromatic. It's got 2-metre pixels in the multispectral area, back to 4 broad spectral bands, but a 1-day repeat coverage and a 20-kilometre swath width. So I'm going to come back to some of the issues there, but you can't listen to an introduction about remote sensing until you see some pictures. So I dug through the NASA archives, and this is the earliest image I can find for Adelaide from Landsat. This is in December 1972, about 4 weeks after the satellite started to produce imagery. And to show you the resolution, that's the Adelaide square mile and surrounds, and you can see it's a little fuzzy, but quite remarkable in its time. We jumped to 2001. I was just going to show you a picture of Hyperion, but that really doesn't do it justice because Hyperion has got all those spectral bands which you can't see, which I can't see. So this particular paper by Arnold Decker from CSIRO shows some enhancement of a few of those spectral bands in Deception Bay in Queensland and shows patterns in the water column which we can't see with our naked eye. What we can see is these massive differences in spectral characteristics. And so MODIS Hyperion tantalised us with this opportunity from space. In 2009, here's a picture from MODIS. This is just using the visible and near infrared. This is in September, so it's the springtime in Adelaide. So Adelaide is green, the way I've arranged the spectral bands. And we see the centre of Australia as brown. And jumping to 2012, Pleiades panchromatic image, which has got about a 43 centimetre spatial resolution over Etihad Stadium in Melbourne, where they play the football and so on. And here we can see the white lines down the centre of the roads from space. So that's a visual view of where we've come from. What I've tried to do in this slide is to show you a few applications of remote sensing and talk about those resolutions and coverages and put my cut on what we need. So, for example, I won't go through all of them. In climate and weather, we generally need low spatial resolution or low to medium spatial resolution. We need medium spectral resolution, but we need high temporal resolution, reasonably high radiometric resolution, and we need global coverage. So we want high temporal resolution hourly or better if we can get it for looking at weather systems. Let me jump to another one. In agriculture, for example, I work in precision agriculture, in particular in precision viticulture. Each vine plant is about 1 metre wide, maybe 2 metres when it's at full growth. So we need pixels which are smaller than a metre to see individual plants. So hence I've got a very high resolution potentially for that type of agriculture. At this time of year, tonight, when there's a cold front that comes through our city, we will have viticulturists scurrying to check for downy mildew in the next 24 to 48 hours, which is a process that occurs on the grapes as they're forming as a result of higher humidity. So if the humidity goes from this very dry condition right now to something a little bit more moist tomorrow, then they'll be worried about that. And they will be out there on the ground, but really they would like to be able to do it remotely. So they need high spectral resolution to see that. They need a cycle of 5 days at minimum and 10-bit quantisation. And they need it locally. They don't necessarily need it for Australia. If we drop to the bottom one, mineral exploration, spatial resolution isn't as critical, but what is critical is very high spectral resolution, at least in the visible infrared and middle infrared. And they need that to look for minerals using a technique called hyperspectral remote sensing. So that's what I think we need. And this picture shows you what I think we've got. Green says it's good. How does that look to you? Yes, green, the colours aren't so good, but green up the top there says, yep, we've achieved that. In the yellowy colours, we're kind of achieving it, but the red is the limitations. For example, in disaster monitoring, we'd really like high spatial resolution and we want it less than every 12 hours. And to achieve that globally is very, very difficult. Or to achieve it over a disaster is difficult from space. In search and rescue, where we have individual people who are lost, injured, we need high spatial resolution and we need a relatively high temporal resolution. So you can see there's conflicts here, which we would like to see resolved. So where are we going? We've had a focus on high spatial resolution for some years now, for the last 10 years. I see that slowing down as we head into the metre and sub-metre area, and so I expect we'll see a return to higher spectral resolutions. So, for example, in 2014, WorldView 3 will launch. It'll have 16 spectral bands and spatial resolutions from 30 centimetres to 3.7 metres out into the middle infrared. The temporal resolution will improve, but it will not improve necessarily from single satellites. It will probably improve as a result of constellations of satellites. So Astrium's Pleiades constellation provides 2-day repeat coverage as of now, because Astrium 2 or Astrium 1B has been launched. I think we'll see some improvements about our ability to see through the atmosphere if we combine optical and SAR systems. So we see SAR systems in space. They don't last as long as the optical and infrared ones, but nevertheless they are there, and we're seeing significant improvements in those. TerraSAR X is a good example of those. Small satellites will dominate the future, I think, from space, with relatively micro payloads compared with the past. There'll be huge competition for position in low Earth orbit, LEO orbit, and there'll be huge competitions for the spectrum for doing the downlink of ever-increasing larger quantities of data. So that's my summary. You guys may disagree with me. You guys may disagree with me. We can have that debate a little bit later. What I'd like to do now is to move on to a discussion of the policy that's behind that. And to kick that off, I'd like Anthony to come over and talk about Australia's policy in this space.
I'm going to talk to you about why I think remote sensing is the most important reason Australia needs to be involved in space. The picture above me uses a little bit of cloud to make the effect a little stronger than it should be. But basically, Australia's in the middle of a whole lot of water. Add that to two other facts which I'm going to give you. Australia is the least densely populated country on Earth, and Australia is the most urbanised country on Earth. And that tells you that there's not a lot in the middle. There aren't a lot of people there, and therefore the most effective way to monitor what's happening in Australia and in the other areas that we're interested in is by satellite. territory in Antarctica that Australia is responsible for is an area almost the same size as continental Australia, that 42% slice that we're responsible for. The maritime areas around Australia that we're responsible for, added to the size of Australia, means that we look after basically an eighth of the Earth, with about 20 million people, most of whom don't wander out of their apartment buildings in Sydney and Melbourne. That tells you satellite information is fundamentally important if we're going to solve some of the major challenges of our time. So, does everybody here come from Adelaide? Anyone from Sydney? Sydney, Melbourne, Brisbane? Okay. All of the weather, particularly in Sydney, Melbourne and Brisbane, is generated... Where did that laser pointer disappear to? Right here. Down there, the Southern Ocean. And there's not a lot down there. And yet, all of Australia's weather is fundamentally dependent on information that comes from down there. If we're going to try and tackle any climate change effects in the near future, some of the most severe effects in terms of social displacement are going to be felt over there in the Western Pacific, an area that Australia more or less has geopolitical leadership responsibility for. How are we going to monitor those small atolls, those small islands effectively? How are we going to get an idea of the magnitude of sea level change? One of the most effective ways to do that is with satellites. I have a newspaper article here from yesterday. Anybody buy The Australian yesterday? The map here is of sea level rise around Australia. It might be difficult to see up the back, for which I apologise, but I'll let you know what it says. Basically, it maps the amount of sea level rise per year around Australia. And the red, which is the highest amount of sea level rise, is 13 millimetres per year. Anyone go surfing? Surfers? A couple? What's a good swell day? Couple of metres? Okay, that's bigger than I can handle, but that's good, you know. Anything from a couple of feet to a couple of metres. And yet we're talking here about rises in sea level measured over a year of millimetres, 1 to 10 millimetres really. How on earth do they manage to make those measurements? Australia's nearly 3,000 kilometres wide, and yet they're telling us that across that distance we're going to be able to tell you exactly how much the sea level is rising to the millimetre. That's a fundamentally important understanding that we get, and we get it because we've got satellites. It's not some guy out there in a rowboat kind of measuring. You know, it's not aircraft. It's way too expensive to send aircraft around there. It's the environmental monitoring satellites that are keeping an eye on Australia. So I've been talking a little bit about weather. I figured that this was largely an engineering audience, so I should put up a couple of graphs. The one on the top is about the northern hemisphere, and the one on the bottom is about the southern hemisphere. Along this area here, you can see how far out they're trying to forecast the weather, basically from now to 7 days out. And then up on the y-axis here, we see how accurate they think they are. Now, many of us disagree with the accuracy of weather forecasters, but this is what they say. The red line tells us what we get without satellites, and the green and the black lines are essentially what we get with satellites. In the northern hemisphere, they're almost the same. That's because there are plenty of measuring stations in the northern hemisphere. The weather in Europe, for example, is largely determined by what the weather in Saharan Africa was like the day before. In the southern hemisphere, we don't have that luxury. What do satellites give us? Well, if you have a look at this, what they really give us is this improvement here. The same level of accuracy that we get, 90% accuracy at 2 days without satellites, we get that 4 days out with satellites. 4 days is plenty of time to change the weekend plans. 2 days, you're kind of pushing it. Satellite information is fundamental to the way every Australian lives their life. And this is one of the main applications, the long-term weather forecasts. This chart shows you some of the satellites which are keeping an eye on weather and climate around the world. What I want you to take away from this is the number of different countries which have an interest in these satellites. They all work together as a coordinated global system, but there are satellites from the US, from China, from Russia, from Europe, from India. All of these satellites cost a lot of money to build, and they're very sophisticated pieces of environmental intelligence about the country and about the Earth. What this says is that international relationships are critically important to the way Australia looks at its space engagement. We simply can't afford to build all of these satellites ourselves. We've just seen that we rely on them, but at the same time, we need to preserve these international relationships in order to actually have access to the data. And that, more than anything else, I think, governs the direction of Australia's space policy. I wanted to say just a little bit about the applications of remote sensing data and why it's so important to have sophisticated satellites. On the left, what you see is a similar diagram to the one we had before, a contrast between some early imagery and some late imagery. But what they've done here is to colour it to reflect the information that we get as satellite capabilities improve. And on the left, you can see a fairly sophisticated analysis that tells us the difference between softwoods, hardwoods, and grass. And on the right, once you add more and more spectral bands, you start to get more understanding about what you're actually looking at. And you can think of this process as getting successively better experts to look at the sort of optical Google Earth imagery that you're familiar with. If you have an expert that can tell that that colour olive green is exactly a palm tree, but if we shift it a little bit more towards the lime green side, then we've got a eucalyptus tree. You sit them down in front of the computer and you get them to kind of have a look at this imagery. That's what the new types of satellites can do automatically for you. And you see on the right that this satellite is able to distinguish between all sorts of vegetation that I've never heard of. Red maples, red oaks, hemlock, mixed conifer. It can tell you the difference between these, and that's fundamentally important for people whose lives are really controlled by agricultural patterns. Think of what you can do if you use this to identify areas where weeds are growing and areas where they're not, or areas of healthy vegetation. That's important to agriculture, and agriculture is important to Australia. So let me say that this is not a new idea, trying to gather information from the air. This is around about the time of the First World War, when the first remote sensing systems were developed. Essentially, they consisted of pigeons with cameras strapped to them, which would fly around and have automatically triggered shutters at various times. I understand that recovering the film was more difficult than actually taking the pictures themselves, as the pigeons would try and get rid of the camera as quickly as possible. We've heard a lot about why this is important, but what's been done about it? All of this different information has come together in a document. If someone can just hold that one up there, the Principles for a National Space Industry Policy. 7 principles which really say what Australia is interested in doing about space and how we're going to get there. Those 7 principles are to focus on space applications of national significance. Anybody guess what one of those space applications of national significance is? Earth observation. Very good. So remote sensing, the sorts of things that we're talking about and that I've been saying are fundamentally important. The other 2 are satellite communications and position, navigation and timing, the same technology that got you here if you're visiting for the first time with your satellite navigation. Assuring access to space capability. Okay, we depend on this information, but that means we've got to make sure that we've got access to it in the future, so that one day you don't wake up and turn on the television and say, well, you know, no weather forecast longer than 2 days because the satellite has run out of battery power. Happens more often than you think. And it's only a sophisticated set of redundancies and that international network that allows us to switch between different providers as satellites reach the end of life. International cooperation, that's a no-brainer given the number of different countries that are involved in space activity and the value that you can get by pooling these different activities together. Contribute to a stable space environment. Space debris is a threat to all of the satellites that are up there. And regardless of whether Australia put up the satellite or somebody else put it up and Australia relies on it, the debris event is going to impact everybody. Domestic coordination is important. Innovation, science and skills development is important. And there's always a link between economic well-being, national security and space capabilities. So I'd be really happy to take some questions after a while on this particular aspect. What I want to stress to you, though, is that this policy development is an ongoing process. So Australia's just starting to realise that maybe space is not all about astronauts and landing on Mars and the International Space Station and things like that. Maybe there are applications for Australia that enhance our productivity and understanding of the environment, and perhaps that's where we should focus. But this is not the end of the story. It's merely the beginning of Australia's engagement with these new aspects of space-related activity. So thank you, and I look forward to your questions.
Thank you, Anthony. We're going to take questions and discussion at the end of this little segment. So, Kimberly, would you like to follow up on that?
Australia is one of the largest users worldwide by both volume and variety of Earth observation data that is provided by foreign satellites. Australian applications of Earth observations from space, which I'll also refer to as EOS, include natural resource management, mineral, petroleum and gas resource characterisation, environmental monitoring and management, disaster management and community safety activities, urban development, and climate and weather monitoring, as Anthony said. And we have some flyers here today, hopefully they've arrived, which describe actually some of the many and varied applications of Earth observation that are going on around Australia. And you're very welcome to come and collect some of those at the end if you would like to read them. Satellite remote sensing is an underpinning capability for many applications, including government programs and services. In the last financial year alone, it was estimated that the Australian government spent on the order of $100 million on Earth observations from space and the associated data processing and so on that goes with that. Which is why it's one of the key space applications that's identified in the principles for a national space industry policy, which Anthony just mentioned. Now, Earth observation is one of the key science areas that I support and provide coordination for within CSIRO. It's a significant area of focus for space sciences, with around 100 scientists working across about 10 different divisions in CSIRO in this area. Now, as you've already heard, Earth observation using satellite imagery is more than just taking photos of the ground. Spacecraft can collect images at a range of different wavelengths, and we can use this to generate a vast amount of information about the Earth. Some of the applications that CSIRO has worked on include mapping forests and other types of land cover, and from this being able to model carbon content to use in the National Carbon Accounting System. Measuring aerosols and water vapour in the atmosphere to help us better understand climate change. Modelling the ground in 3D and mapping water catchments, dams and rain runoff to better manage our water resources. Mapping soil salinity and helping farmers to accurately estimate the amount of feed in their pastures, how quickly that pasture is growing and the pasture quality. And they can do that by calculating variables like protein, fibre, oil, starch and other components in pastures based on what they see from the satellite imagery. We can assess the effect of the runoff of sediments, including pesticides, herbicides and fertilisers, on the Great Barrier Reef corals, and that's actually what the image on the right in the middle there shows. So that there is the Great Barrier Reef, and we can see runoff out here, which until they considered that imagery, they didn't actually realise that the runoff extended so far out into the reef that it is quite obviously having an effect. We also undertake disaster monitoring, like mapping floodwaters and tracking bushfires through the use of thermal imagery. Some of you may be familiar with the public Sentinel bushfire monitoring website. This is a snapshot from Sentinel, and that system was actually developed jointly by CSIRO, Geoscience Australia and the Defence Imagery and Geospatial Organisation. We also use Earth observation for exploring for new minerals, and we can even use satellite imagery to map the variations in vegetation which actually aren't visible to the naked eye, so that we can better understand and protect the habitats of our native animals. Much of the satellite imagery that we collect and manipulate is managed through national facilities that are led by CSIRO in conjunction with other research organisations. These facilities include the Terrestrial Ecosystem Research Network, or TERN, AusCover facility, which is an online data archive and access system, the Integrated Marine Observing System, or IMOS, satellite remote sensing facility, and AusScope Grid, which is a similar system for earth science related applications. And it's very important to note that CSIRO, and indeed Australia, does not own or operate any of its own Earth observation satellites. We rely very heavily on the strong relationships that we've established with foreign space agencies like NASA, JAXA and DLR, and international organisations, as Anthony mentioned, to access the satellite data that we require. In return, though, CSIRO actively supports the satellite Earth observation missions of other nations through the provision of services including satellite calibration and validation from the ground, which we do out on our salt lakes amongst other locations, and we do provide some data downlink services. Now, although Australia doesn't own any of its own scientific satellites, in addition to providing expertise on applications of satellite imagery, our scientists sometimes also contribute to scientific instruments that are on board foreign science missions. One project that CSIRO is currently involved in through our Australian Centre for Precision Optics, along with other Australian researchers and NASA's Jet Propulsion Laboratory, is building some of the high precision optics for a laser measurement system on NASA's next Gravity Recovery and Climate Experiment, or GRACE satellite. So in reality, the gravity field of the Earth is not perfectly uniform because the Earth is not perfectly round. And the GRACE mission consists of two satellites that fly one behind the other, separated by 220 kilometres. And with the slight variations in the gravity field as they move around the Earth, they move slightly further apart and slightly closer together. And if we can measure that displacement very accurately, which we'll be doing with this laser system, we can calculate the fluctuations in the gravity field of the Earth. And why would we want to do this? Well, because whenever there is something like an earthquake, or the polar ice caps melt a bit, or groundwater is depleted from a particular area, this affects the Earth's gravity field. For instance, in this image here, what we can see is the effect of the 2004 Boxing Day earthquake and tsunami. And on the right, we can actually, via changes in the Earth's gravity field, we can track the gradual loss of water from the Murray-Darling Basin over a period of about 4 years. And that was actually done by researchers at the Australian National University. There are also a number of other interesting projects like this going on around Australia, a number of which are funded under the Australian Space Research Program, which this GRACE project is also funded under. These projects relate to small synthetic aperture radar satellites, satellite sensors to monitor greenhouse gases, and the space-based National Wireless Sensor Network, which you may have heard about already, which is a project being led by UniSA and which CSIRO is also a partner in. Now, Earth observations from space are used widely by numerous federal and state government agencies around Australia, research institutions and the private sector, with organisations within the government like Geoscience Australia, the Bureau of Meteorology, the Department of Climate Change and Defence routinely acquiring data from dozens of foreign satellites. As I mentioned before, our current government expenditure is about $100 million a year on Earth observation, and we do expect that to increase in the future. Now, this slide actually builds on one of the slides that David showed in his introduction. Australia's dependencies on EOS data, particularly the government's operational dependencies and those of the research and development sector, were assessed recently in two separate studies, one by Geoscience Australia and one by CSIRO, which another of our speakers, George, was also heavily involved in. And these studies found that there are over 100 currently active government programs and services that depend on Earth observations from space to some degree. And we get this data from more than 40 foreign satellites. Now, these two studies determined that the data types that are listed in the left-hand columns of each of these tables are the highest priority data types for Australia at the present time. And the right-hand column shows the risks to the continuity of these data types over the next 5 years. And that risk rating considers the likelihood of a data gap before 2015, the availability of alternate data sources, and the current and projected data usage levels. So just considering this, I'll show it again if we get the time to talk about applications around disaster monitoring. But you see that there are a couple of particularly useful data types there, the medium resolution optical and the synthetic aperture radar, which are priority data types for our country, but which also face some risk of continuity in the next 5 years, which brings us around to the need for public policy in this area that Anthony has mentioned, because our international relationships are absolutely vital to securing that data in the future. Thank you.
George is going to take us through a slightly different perspective on this and also provide an international component to the discussion, I hope.
You hope. Okay. I will try. I just wanted to pull on a couple of things that people have said, because I think there's been some really interesting points. I'm going to start with Scott's point that these satellites are time machines, and that's something that really didn't occur to me until recently. But if you look at an archive like Landsat, it goes back to 1972. So if you want to assess an environmental impact, now you have 40 years of history. You can look back at what the Pilbara looked like in 1975, and you can compare it to what it looks like now that Rio Tinto has gotten at it. So that's a really important point. Another general point is that I think for space in general, and this applies to Earth remote sensing, but also to Mars, to the Moon, data is the only thing that we're getting back for a long time. And so I think this is a vitally important topic. Even if we get back a small Mars stone or an Earth moon stone, it's still really data. We're not getting a commodity back. So this is the essence of what space is delivering for humanity. I mean, besides the experience for the people and the robots that go, this is the essence of what we get back from all this space activity. So I think that's a vitally important point. In the time machine spirit, I really enjoyed Dr. Bruce's summary, and what Landsat can tell us is that in the 80s, My Sydney Swans moved to Sydney, Corsley, and what he pointed out nicely was that the new Pleiades satellite can show them winning the flag this year. So very handy for satellites, a very good application indeed. I can't underscore enough how I agree with Anthony and Kim about the climate monitoring. The example of GRACE is a great one. If you look at water ice loss in Greenland or the Himalayas or Antarctica, you can't go there and measure that in any meaningful way, but with the GRACE satellite, you can tell the way that those glaciers are shifting, and that is a fundamental piece of data for climate monitoring. So what I'm going to talk about really as briefly as I can is about the EOS sector and what we do internationally. So this is a very coarse sketch of the EOS sector. You have meteorological which is all the weather satellites, and also increasingly climate satellites. And then you have, and that's about a third of civilian systems, and then you have non-meteorological satellites, which are your land cover, land mapping satellites, plus a number of R&D satellites. And then you have commercial providers, like Pleiades, for example, is a commercial provider, and so they're in it for the business. This excludes the military sector, which is a whole other sphere, shall we say, an important one. So the first group I do a lot of work with is the Committee on Earth Observing Satellites, and this is, there's a lot of words on here, but basically it's about 30 member space agencies from around the world. Tends to be the non-meteorological ones, although some of the meteorological agencies are also a member of CSIRO. Established in 1984 and basically charged with trying to coordinate the use of these satellites, trying to make this technology, which is amazing and fascinating, and I love it, useful for humanity. And that's really the broader goal of CSIRO. And part of realizing that is, optimizing benefits, serving as a focal point for coordination. So like Anthony mentioned, the Space Policy Unit here is coordinating. CSIRO is trying to do that on a global level. So give a forum for people who operate satellites to come together, talk about what they're doing, and cooperation is a lot messier than you might hope. As a software kind of guy, I'd love it if it was as easy as writing some good software, but there's a heck of a lot of barriers involved. And so we're seeing promising signs of cutting through that. But that's what CSIRO is generally working on, trying to optimize the use of these satellites. Part of achieving that is it's partnered with another group called GEO, the Group on Earth Observations. And GEO is working on Earth observations, not just from satellites, but also on the ground, from aircraft, in the ocean, all different domains. But CSIRO has agreed to coordinate the satellite side of this GEO system, which is very important for a number of reasons. Satellites are an important data source. Often the georeferencing systems can't be delivered without space assets. So, understanding like a GPS, for example, to understand where observations are taken. CSIRO is working with this GEO to coordinate. One of the key goals of GEO is to connect to user communities. And so I'm going to just talk quickly of a few examples. The first one is on the climate side, and so they're working with a group that's setting up a global climate observing system. They have this is the scientific community, the researchers who want observations. They've said, here's the parameters we need to observe. Of those parameters, a huge percentage can only be observed with satellites. And so we work on delivering those, CSIRO works on delivering those communities the data that they need. So, for example, ocean color, sea surface temperature, atmospheric, land maps, all kinds of things that are important in climate study. Another outreach that GEO is doing to a user community is forest observations, and Australia is very involved in Indonesia, in this case, in Borneo, as are a number of countries, providing satellite data to those countries so that they can set up a global a national carbon accounting system and understand how their carbon cycle nationally is working, and then try and apply some economic incentives or disincentives to manage it. Again, these are foresters. They have no idea about satellites, so GEO and CSIRO are trying to bridge the gap between forestry and the technology that they need to achieve their goals. Someone mentioned agriculture. Was it you, Doctor? Yeah. So GEO is also involved in a global agriculture monitoring system. This is a slide I stole, so that GLAM is global agriculture monitoring. And again, these are economists and agronomists who are interested in predicting prices of food. There's been some huge spikes in food prices in the last 3 or 4 years. Fundamental staples like rice doubling, tripling in price. And for people who live in Adelaide, that may not be as big a problem, but when that's the only food you have and that takes 40% of your budget and all of a sudden it doubles in price, that's a huge issue. So we're working with these groups to try and, again, get them the satellite data streams that they need to go into their models. One that's a little bit closer to home and that Anthony's Space Policy Unit has been involved with is a regional effort that we've been pushing to prepare Asia-Pacific for to be ready for these satellite data streams. There's a lot of countries in Asia-Pacific, and there's a lot of different skill levels, national skill levels. Australia is a very sophisticated user of satellite data. Other countries don't have the capacity, don't have the resources, the wherewithal. So Australia is trying to promote this regional readiness activity. And by doing that, as Kim mentioned, we're adding value for the satellite agencies who want to connect with their users. And therefore, they'd be more inclined to continue to provide us with the data streams and information that we need. So that's a very brief overview of the international activities. What it left out is the whole weather side, which is coordinated under the United Nations, and that works very effectively. That is a very effective data exchange mechanism. Some of these other projects are still getting going. And that's all that I had.
George, stay there. What I'd like to do is to open this up to some sort of discussion, and maybe I could put a question either to the panel or to the audience and say, well, okay, Australia has been using this remote sensing data since 1970s very effectively, very in a sophisticated way. What's wrong with keeping going with that? Why can't, instead of building our own sensors or launching our own satellites at costs of hundreds of millions of dollars, why don't we just continue to do that? Keep our relationships going well with the international community and keep proceeding with that. Use that hundreds of millions of dollars for benefits to society on Earth. So I could put that to you, but first of all, I'll throw it to Anthony.
Well, the funny thing is I agree with you completely. The problem that we face as a global community in terms of satellite observations is that there are too many of them, not that there are not enough of them, right? The latest Japanese weather satellite called Himawari will download a gigabyte of data every 10 minutes. Think about archiving that over decades and the sort of communications and IT infrastructure you need not only to store it, but to be able to find answers in it. And sifting through the big data that's being returned by all of these Earth-observing missions is going to be the big challenge of the next decade. Australia is really good at that. We've been really good over the last 40 years at making do with other people's data, so we have some very sophisticated ways of storing and searching and applying algorithms to the data that we do have. So I'd say that that's a very sensible course to follow for the next 10 years of being a responsible member of the international community by providing these services and helping to sift through the data and making sense of it.
I would agree completely that our problem at this point is a combination of competing national priorities that are very ineffective and inefficient, but also that we need much better ways of archiving and accessing all of these data, particularly in areas like disaster management where we need very rapid access. We need to get hold of the data and then process it. But processing it really isn't the goal either. We need to get those data in the hands of end users in a very rapid fashion. And as we have more and more data piling up in these data repositories, actually getting useful data in a timely fashion to people who need it becomes more and more difficult.
All our hopes are riding on you, Anthony, and the Space Policy Unit. Don't let us down.
No pressure.
Yeah, exactly. Just to take on this issue of whether or not Australia can continue to freeload, to be honest, speaking as a New Zealander, at the very least, if we do it, we will have to build a new set of relationships. You can see it in perhaps defence first, that just replacing the systems that you have up there for the US is consuming almost all its budgets and resources, let alone putting up new ones. more infrastructure you put up in space, the more you have to keep supporting it, and the more it just eats all your budget. If you want new stuff, increasingly, I guess you'd have to look to countries like China or India, which are on the upside of growing their systems, and that means you have to build a whole new set of international relationships, which we haven't really yet started on. But even then, they're going to have the same problems as well. So eventually, somebody is going to have to step up to the plate. It's not a long-term... Well, it might do you for another 20 years, but I don't think it's not going to be a credible long-term strategy.
Let me just say a couple of things to that. And the freeloader tag is one that Australia is kind of tagged within the international community from time to time. Part of the problem is underinvestment in space capabilities relative to other countries. Part of the problem is over-expectation. Australia was the fourth country with a significant help to launch a satellite to orbit from its own territory. And so people have expected Australia to punch way above our weight ever since then. Considering our GDP and our geography and our demographics, that's simply not possible. You know, we have to be realistic about what we can achieve. But I think the major problem and the major reason why the freeloader tag is a little inaccurate is because Australian contributions, by and large, are by individuals in their areas of expertise, and they're really valued contributions to the international community. But the problem is they're seen as individual contributions. Because we don't have organisations on the scale of NASA or the European Space Agency to really give a badge to their activities, they're seen as individual contributions rather than Australian contributions. So the researchers could be from CSIRO or from the Department of Climate Change or from the Department of Industry, but they're seen as individual contributions and not an Australian contribution. And I think that's one of the reasons why there's this international perception that Australia is not doing anything at all, when in reality there's a range of things that we are doing that I think are more or less in keeping with our place in the world.
Anthony, you're mostly consistent with what I've experienced. I will say that people I meet are somewhat surprised that Australia doesn't have that badge, that space agency, that, what would it be, ASA, or anyway, whatever we want to call it. And so I think, you know, that there is room for ambition there for Australia, and I don't think that should be ruled out. But on the freeloading side, I think you're right. We're power users in the satellite data area, and not just within Australia, but we also spread that expertise across the region and give it back to these satellite data providers. But the obvious downside, I think, to not having a physical investment is when something comes to a head. So the example of Antarctica, for me, is always one that I think about. The Australian claim is 42% of the Antarctic territory. The countries who signed that treaty agreed not to exercise those claims. But if one day they did, we have no real way of monitoring that territory from a defense perspective, from an activities perspective whatsoever. And so if the European and American and Japanese satellites that we use to monitor that Antarctic claim are denied to us because there's some other negotiation going on, then all of a sudden it becomes a very material... And I don't mean that we want to send in the tractors and start digging up Antarctica. In fact, quite the opposite. The Australian national value set probably is a conservation and preservation value set. And so if we want to project that kind of influence, we need to have these tools and assured access to them. Now, whether that means buying a lot of satellites and launching them, I don't know. But that's an outcome I see that is risky with the current strategy, that we lose some autonomy there. Not to mention the whole Southern Ocean, the Indian Ocean. There's giant swaths of water that we have responsibility to look after. So.
I guess my question follows on from that. One thing we haven't touched on tonight is sort of national security, and one thing that the Principles for National Space Policy points out is that Australia will continue to rely on our international relations to provide that national security. Is that a sustainable way to move forward and depend on that for the future?
I suppose I should start, and then I'll leave it to my colleagues to say a little more. Let me say two things. First, this document is described in the jargon as a whole-of-government civilian space policy. Let's deconstruct that for a second. Okay, it's a civilian space policy. It doesn't really touch on any of the national security issues which are there. That's great. But it's a whole-of-government policy, which means that the Australian government as a whole, which includes the national security elements, are comfortable with this. So that's the lens through which you have to read it. It doesn't touch on those things that are solely concerned with national security, but it's consistent with anything that we might think about in terms of national security. As for the broader implications of your question as to whether Australia should rely on allies or go it alone in terms of its own national security, I have to confess that's a question above my pay grade to really answer. And that's a matter for Australia's broader defence policy and how that ties in with space policy. So I'm sorry I can't tell you any more, but that is a very relevant question. Yeah, we'll say a little more.
As an outsider, I would just like to say that, in my view, the definition of national security is undergoing a very large change and broadening. And we used to think solely of strictly civilian activities, strictly military activities, but I think around the world, people are beginning to recognize that climate change is a national security issue. Global warming, sea level rise, the potential for famine, for civil unrest, all of these things, I think the definition of what we used to think of traditionally as military space and civilian space is perhaps becoming much more intertwined. And I think we need to perhaps, in every country, think of a larger perspective of how we define national security. And I think national security includes a great many of the traditionally civilian type things that I see the world as blurring those definitions.
Are there any more questions or comments from the audience? We'll take two over here, and then we'll close that off and we'll finish on an application.
I'm Jeff Kasparian from the University of South Australia. Kimberly, you put up a slide that indicated the things that were important to Australia from the point of view of Earth observation, and you listed that some of them were okay, so they had a low risk in terms of continuity of data, and there were a couple up there that were in that very high risk category. And I just wonder, from the panel's perspective, what is it that we can do as a country, given the normal fiscal constraints that we're dealing with and so on? What can we do as a country to influence those things that we think are therefore important? So we either decide that they're really not important, or in fact we know that they're important and then we do something. And I'm sure part of that answer is always money, right? But I just wonder what the process might be from this point in time, recognising and accepting that let's say that your table was accurate. What is it that we are doing or that we perhaps should do in order to address those gaps, those important gaps?
Well, there's a couple of things that we're doing to address this. What we were looking at when we identified the high-risk data types was to look at where that data might come from in the future, and looking at perhaps needing to expand the relationships that we currently have into as non-traditional partners or new satellites with agencies that we don't necessarily deal with so much at the moment, but acknowledging that they could be very important sources of data in the future, and then working through the Space Policy Unit, Foreign Affairs and so on to build the relationships that will secure that data for us. Another thing that we're also looking at is our own ground infrastructure for Earth observation, ensuring that we continue to have the capacity to receive the data that we need, and to manipulate it, store it, transport it, and so on, because we have a very ageing infrastructure in this country, and that's something that through the National Space Policy development process we've been looking at very carefully as well, and identifying, obviously, to do everything that we want to do would take money, but there are also things that we can do right now with the resources that we have to try and improve our situation, and to start planning for the next 5 to 10 years what we might do to address that situation as our budgetary situation improves.
I was involved with that CIOTA study as well, and I can say I think one of the things that would help us the most, and this is a bit tongue-in-cheek but not totally, is to join ESA. As an associate member, as Canada has done, even though we're not in Europe, ESA is investing billions of euros, although the budget's been knocked down a lot by what's going on in Europe, but still that only slows the programs and doesn't stop them. But the systems that they're building in the Sentinel and GMES range have great performance. They're designed to deliver societal services. That's the purpose of the GMES, as opposed to R&D. These are operational missions. And so I think when Kim says new relationships, that single relationship and building that is vital. And we know that Europe is called a number of times and no one answers the phone because there's no central coordinate. Well, there is now, but there hasn't been a central coordinating body. And so I think that's the kind of thing that we can leverage, a huge investment by the Europeans, who are friendly allies of ours, with a small investment here, and without maybe building ground infrastructure. That might be one way to do it. But I think that would solve a number of those red boxes on that chart. It doesn't get you a brand new global hyperspectral sensing mission for a number of years, but it does get you services.
Joe Pelton, former dean and former chairman of the board at the International Space University, and I'm enjoying being here in Adelaide very much. I guess my question is, what, looking at climate change in particular, are we missing? Professor Roger Franzen has suggested that we don't have sufficient capability to measure on a global scale heat absorption on a global basis. It does occur to me, taking Scott's comments into account, that if we were to work better together as nations, like kids are supposed to work together, what could we do to create the best tools possible to address the issue of climate change, create all the tools we need, and not duplicate capabilities we don't need. And this could be for processing as well as hardware. So perhaps George could start.
Well, if I put my forestry hat on just very briefly, I'd like to see a P-band SAR satellite. But I think there's a lot of technical solutions, and we probably would end up picking some winners and getting some of the wrong answers there. I think the biggest thing we're missing is assured continuity of observations and with consistent data formats. I mean, Landsat is a great example of that, but we need that across a number of those climate variables, because climate is a long-term activity. It's a long-term study, and so we can launch as many 1, 2, 5-year research missions as we want and develop new sensors, but probably we need that continuity. I think there's some hope for continuity of some specific climate observations in geosatellites. So we currently measure things. I'll take the example of lightning from low Earth orbit, and that's been an R&D project in figuring that out. But now that we know how to look for lightning and that's a real marker of storm activity and a lot of other things. We can put an instrument on a geosatellite that can sustainably deliver us a long data record, the whole disk of the Earth, every 15 minutes. You know, a huge step up in continuity. So I think for climate, that's what we need. We need to be assured that if we get a new sensor and it has a good application, that we can have it for a long time and uninterrupted. Another good example is sea level. The JASON series of satellites have had a very precarious programmatic history, and we've, through CEOS, for example, and other organizations, struggled to keep that continuity. And now we have a real graph of 20 years of sea level, and it's going up. But if that gets interrupted, then by lack of continuity, then we have a break in the graph, and then the record needs to be reestablished and recalibrated, etc. So I think that's probably one. I'll just say one other area, direct carbon measurements. So building on CO2 measurements like GOSAT and NASA's OCO mission, which failed the first time but is being relaunched. There's a lot that can be done in that area. And in terms of improving resolution, temporal frequency, spatial frequency, we're not going to be detecting campfires in the wilderness, but we might be able to see CO2 emissions from large urban areas, industrial areas, and sort of really get to understand the carbon cycle a lot more. So.
OM will have the lightning mapping capability. Is that what you're talking about? Or?
Yeah, they're the first ones, and UMETSAT is also working on lightning mapping. And so that approach just gives us way more prospect for continuity. And
I don't think we have time to actually run our next segment. So what I'm going to do is a little bit different, unannounced to Scott and Kimberly. What I'd like you two to do is to wrap this up, but by using disaster monitoring as a sort of an example. So we've got about 10 minutes left. So if you could each talk about disaster monitoring, its benefit or not for society, and what's needed.
Especially in disaster management, the key issue is timely and useful information. And I would say also partly to what Joe raised, that we're very good at designing sensors and operating systems and collecting data. We're not so good, but we're getting better at turning all those zeros and ones into useful information. And particularly in the more complex areas of climate change, disaster management, the timeliness issue, those are difficult problems, but we're getting much better at it. What we're really not good at all at is turning that information into real knowledge and practicable action. And I think that's really an area that we need to focus on more. People in science and engineering and the agencies want to focus on the next scanner, the next detector, then the next highest bit rate. And we have to do that, but in the end, it's got to be useful to somebody in a timely manner. In disaster response, and I work a lot in this area, time is the enemy as much as the disaster itself. And we only have literally a few hours and days to have the opportunity to actually save the majority of people who can be saved. And so getting useful information into the hands of the people directly in the field in a format that they can use is a huge obstacle that we face right now. And we can collect lots of data. We're really good at collecting data, but turning that into actionable intelligence in a very quick time frame is something that we need to do a lot better at. And particularly in the disaster management and response world, we're talking literally hours of collecting the data, processing the data, and actually getting it into the hands of people who are not us. These are first responders, volunteer firemen, volunteer responders, and so somehow we need to do a much better job of turning what we do into things that the practical end users can actually utilize. And in the disaster world, it's a very special case of getting actionable intelligence into the hands of the responders under very, very difficult response conditions. But I think that generally goes across the board for all of the applications. And it goes back to Joe's point of climate change. We still in my country have a significant fraction of the elected members of Congress who don't think it's happening. And so we need to turn zeros and ones into useful information, and we need to turn that into knowledge and actionable intelligence, and that chain is a very difficult thing to do. In the disaster response world, it's even harder because we literally only have hours to be able to save people's lives.
So I would just like to note before I move on that disaster management doesn't just include watching while the disaster is happening and the first response phase. It does include prevention and mitigation, preparedness, then monitoring it, responding, and also recovery. And we've had a number of pretty major disasters over the last 5 years or so. We've had the Victorian bushfires, which we used Earth observation for very heavily. Cyclone Larry, which struck Queensland in 2011, and the Brisbane floods, also 2011. And what I wanted to show you here is just a fairly basic economic assessment of how EOS actually benefits us in disasters. This is based on a study that was done by ACIL Tasman in 2010 to estimate the actual economic benefit of EOS to various aspects of our economy, including through disaster management. And managing disasters and emergencies in Australia costs us about $2 billion a year. That's disasters or emergencies which exclude the major disasters which I just mentioned. They estimated that using Earth observations from space actually saves us about 10% of the cost of a disaster. So what I've done here is a summary over a 5-year period where we can save $1 billion by using EOS on disaster management and emergency management. But then if you consider what our major disasters cost us, the Victorian bushfires cost $4.4 billion. The Queensland floods and Cyclone Yasi cost between $6 and $7 billion in damage to public infrastructure. And we suffered significant losses in terms of productivity of the businesses that were disrupted during Cyclone Yasi and the Queensland floods. They estimate that cost to be over $4 billion. So using the assessment that ACIL Tasman offered, we're saving several billions of dollars over a 5-year period using EOS for disaster management. And a lot of the imagery that we actually get provided to do that is actually provided free of charge or at very low cost to us. We still have to receive the data and manipulate it, have the staff to know how to use it and process it. That does cost us something. But compared to the savings that we can actually achieve by using this data that's available to us, it's an incredible economic benefit to our country.
There's a fascinating new development in all of this, which is called citizen science or participatory remote sensing. And I actually worked on Cyclone Yasi and the Queensland floods from my office in North Carolina in the United States. And I work with a volunteer group called the GIS Corps, which is a group of voluntary remote sensing GIS, GPS specialists. And I actually worked on that project for the Australian Red Cross from my home and office literally halfway around the world, off and on for a period of 2 weeks. And there were people all around the world, in Cyprus, in Germany, in China, in Europe, Canada, and the United States, who were volunteering their time and working together in a very, very interested fashion that we're delivering classified data, satellite image analysis into the decision-making process literally around the world. And we were passing data from the U.S. As the time cycles worked around the world and turning data into the Australian Red Cross. And so there's a lot of really interesting things going on where a lot of the traditional boundaries of how we can do this type of work used to be in big laboratories with false floors and huge computers. And literally we had 24 people working around the world on that project, delivering very highly classified, deeply analyzed data into the decision-making process around the world. So there's some very interesting new developments, and I just wanted to say that, it's interesting you mentioned Cyclone Yasi, because I was actually working on that literally half a world away.
Thank you, Scott. I think that's a very positive note on which to finish the conversation. I'd like to thank you for attending and listening, and I'd like us to thank our speakers, Scott, Kimberly, Anthony and George, for coming from interstate, coming through the heat and putting the effort in and talking to us. I'm sure we could keep going, but I'd like to say thank you very much. Thank you.